When an aldehyde or ketone is treated with sodium borohydride, that starting material is reduced to make an alcohol. Here are a couple of examples. It fits our definition of reduction because we have a decrease in the number of carbon-oxygen bonds and an increase in the number of carbon-hydrogen bonds. We can understand this reaction in terms of nucleophilic addition to carbonyl. Take a look at the carbonyl group. The carbonyl group is polarized, partial positive on carbon, partial negative on oxygen. And nucleophiles are attracted to the carbon, which is electron deficient, while the pi bond breaks. This is exactly what happens in the sodium borohydride reduction of aldehydes and ketones. On the left, I've put our picture of nucleophilic addition to carbonyl, and you'll see that the sodium borohydride reduction of aldehydes and ketones is really very similar. The borohydride reducing agent transfers a hydride with a pair of electrons to that carbonyl carbon, while the pi electrons of the carbonyl are used to form a bond with boron. The resulting product is the reduced carbonyl group with the boron associated with oxygen. If it starts out as sodium borohydride, then there are 3 hydrogens left on that boron. Because there's still 3 hydrogens attached to boron, this same reaction can happen 3 more times. So when we're done, there's 4 of those guys attached to boron. The only practical reason for noticing that this happens 4 times is that you really only need to use 1/4 of the reducing agent in the lab on a molar basis. And in a protic solvent like methanol, which is typically used, this complex comes apart to release the alcohol. So overall, it's a simple 1-2 addition to the carbonyl group. If we start with an aldehyde, we end up with a primary alcohol. If we start with a ketone, we'll have a alkyl group here, and this will be a secondary alcohol. Just to make clear, because I omitted it inadvertently, I'll put the negative charge on boron because this is negatively charged throughout, and we know that this is a sodium borohydride, so there's always a counter ion. One last thing, it's worth mentioning that this can be water rather than an alcohol. There's a very similar reducing agent that works the very same way. The reaction I've shown here uses sodium borohydride. Lithium aluminum hydride is an alternative. These look very similar and are similar structurally, but there's a huge difference in the laboratory. Sodium borohydride is a relatively mild reducing agent for polar functional groups, while lithium aluminum hydride is a very strong reducing agent. So it's much less selective, reduces other polar functional groups too, like carboxylic acids, esters, amides, and it's a bigger challenge to use in the laboratory. You must use reaction conditions that have no protic solvents of any kind around, because lithium aluminum hydride reacts with protic solvents to release hydrogen in an exothermic reaction that causes a fire, typically, perhaps even an explosion. So I've simply swapped out boron and put in aluminum, swapped out sodium and put in lithium, and everything else is the same until we get down to the last step, and typically that last step is done with water. This must be done in a second separate step because, as I mentioned, lithium aluminum hydride reacts violently with water. Whereas using sodium borohydride, we'll typically use methanol as a solvent, and the hydrolysis in the last step occurs as the reaction proceeds. And while we're talking about reduction of aldehydes and ketones, it's worth mentioning that they can be reduced using hydrogen and a metal catalyst. Very reminiscent of what we saw with alkenes. Again, aldehydes make primary alcohols. The reagents are hydrogen gas and a metal. A variety of metals can be used. Nickel is common, platinum, palladium, even rhodium. Ketones make secondary alcohols. Aldehydes and ketones are reduced effectively using sodium borohydride, or the much stronger lithium aluminum hydride, or an entirely different reduction process altogether that uses hydrogen gas together with a metal catalyst. And without going into the mechanism in detail, let me just mention that this is not a nucleophilic addition to carbonyl. The mechanism of this reaction is very similar to the reduction of alkenes using these same kinds of conditions. The reaction is dependent on hydrogen gas reacting with the metal surface to split the hydrogen molecule into two atoms. So the molecules of hydrogen literally break apart to form hydrogen atoms that are bonded to the metal surface. And that interaction with the carbonyl transfers two separate hydrogen atoms to accomplish the reduction, which occurs in two steps. So there you have it. Aldehydes and ketones are reduced effectively in very high yields using sodium borohydride, or the much stronger reducing agent lithium aluminum hydride, or using completely different conditions, hydrogen gas with a metal catalyst also reduces these carbonyl compounds to make primary and secondary alcohols.